Unfortunately, previous video broke at 40 minutes. Good morning again. Namaskar. This is Engineer Suraj Singh speaking from Bharat, India on this day, January 25th, 2022, 4:36 morning, and this is Tuesday. मैं सूरज सिंह सिविल इंजीनियर भारत इंडिया से का दिन पिछला वीडियो टूट गया 40 मिनट पे, अभी भी सिग्नल्स डाउन, श्योर नहीं, स्टार्ट नहीं हुआ, 1 मिनट हुआ. लेट मी सी व्हाट हैपन्स. It's very poor performance by Airtel. Means framing is very poor, videos are very poor, signals are very poor, everything is poor. I don't think I'm able to continue, but let me see what happens. It may break again, beyond my control. Well, let's enjoy whatever we have. As I was talking in that, how to enjoy what to enjoy. I was talking about title, quality works, concrete specification, etc. All this, and we are talking about we're talking about what to do in such cases. Our quality system, about quality, about products, as usual we say. I was talking about what's happening in other countries, what happened in past. Because I am witness to that. I experienced that. In fact, I learned a lot from there. I can say I could not ever learn in my country had I not been there in Gulf or in Middle East. I worked in our country also in beginning of my career, and still I am here. But I am not actively involved in construction, to be very frank. For many years I have not been involved, and whatever I see, when you walk around or when I see something, I talk to colleagues here, it brings disappointment to me. And not because maybe there's something wrong somewhere. It lies in culture, If you see work culture here, work culture is very different. Monotonous culture, no sense of anything. Forget systems, forget quality. Means there is no loop of anything. So as I'm saying, red lines exist. Yes, they exist, but we have to solve it. If engineers cannot solve it, no one can else solve it. I say, can we know and apply quality standards complied other overseas, for example in GCC countries on buildings and plant facilities? I refer to GCC countries and Middle East countries because I have worked there. I have not worked in West countries or in Far East countries. I have not worked in USA or you can say England or Europe. But wherever I worked, there was none of their own documents. All were imported one. American codes, British codes, European codes, and systems and procedures and everything. Exposures means if you have long exposure in Gulf countries or Middle East countries, you have diverse Western experience which you can't even have when you work in West. If somebody works in USA or in England in engineering, I think it won't be equal to what you work in Gulf countries. Gulf countries, I mean not only actually GCC countries but also Middle East countries like Iraq and like many other countries around. Variants of technologies depending on what codes you use. And there is worst situation also I have seen in some parts of these countries, worst quality also and best one too, both. Depends on what sort of organization management there exists. I have been fortunate enough that first of all I have been in many countries with many companies, many organizations, public sector as private sector, both contracting as well as engineering. I'm not extensive designer, but opportunity I have got through engineering that I have been to designs also. I'm not expert in designs, I'm not having very good software knowledge of designs. But engineering is interesting to me because engineering gives you advancement. Design may not give you that advancement, that's also true. Because design has got limitation, no designer is interested to work on sites, and that's another problem. Our designers think that if they work in designs only, they are structural engineers or they are designers. But my approach is a little different. I say designer is an excellent engineer, but you are not an engineer if you are not on site. And that is what point. Because if you want to teach others, you have to be on site. You cannot teach through drawings. You cannot teach through writings. Yes, you can teach to some extent. But teaching goes to site. First you have to learn. First we have to learn. Then we can teach. What we learned in university, that is not engineering. That is engineering education. But what we learn on site, that is factual. Because you know where is mistake. When you commit mistakes on sites, we can know this is mistake, but a worker cannot know. An ordinary site worker cannot know. An ordinary site supervisor cannot know. We have to see what mistake happens and we have to pinpoint it. We have to pinpoint it and correct it and then to teach them this is a mistake. Or we have to learn from them. How they do, we cannot imagine activity orientation. We cannot imagine how can performance be done. Just sitting in the office and assuming everything. Design is one part. Design is mechanized now, is software based. Very little input is required. But whatever it is design. And if I design something and I don't know what problems can be faced on site, then what's the meaning of design? If I do not understand what problems my colleagues on site would face, I just know what I have done, you follow it. Yes, they would follow it. They will follow it happily and they come into problems, trapped. When they are trapped, work is held. Then whose accountability it becomes? If I do not know how work is done on site, I think my design is incomplete. It's very easy to show this is reinforcement here, this is detailing here, follow it. But can I make sure or can I guarantee that the detailing is constructible? My design must be in proportion to constructability coefficient. If constructability becomes a problem because of my design, the design is inefficient, I can say. It's not perfect. It's not optimum baseline. We may show so much details, miss something. You're a side guy, you follow what I'm saying. They have to follow, it's of course right. But you are also a side guy, maybe you're sitting in office or designing, you are also a side person. You work for that site. Means you're not on site, but you work for that site. You know what's going to happen. You should have a clear picture in mind. How shall it work? You should know that, not simply instructing on drawings itself. Maybe in beginning it doesn't happen. When you start your career, it doesn't happen. You're a budding engineer, and I'm finding another problem nowadays that those who get some more education, for example, ME or senior BE, they think they have to sit in office and work. They're structural engineers. Okay, you are a structural engineer, but remember, you are an engineer only when you do something. You do face problems, only then you can be. If structural engineers sitting on a structural engineer forum raise questions about something which is not becoming a question, which is not a become question, unbecoming question, if you don't understand soil, if you don't understand rock mechanics, if you don't understand basics of engineering, how can you say that you are an engineer? It's very simple to say that I am a structural engineer, I am a design engineer. It's so simple to say, but really are you? Without producing any works on site, how can you call yourself even an engineer? Forget structural engineer. A structural engineer is little higher, and a structural engineer must know what should be problems, what can be problems, and how to find solution to them. And without exposing oneself to site conditions, you cannot learn engineering. I don't consider books engineering only. I consider real engineering. Being on site doesn't mean you're site engineer, not at all. And being in design's office doesn't mean you're a design engineer. Constructability engineer you should be. Design constructable engineers. Are you? I'm not saying design engineer alone. You have to be design engineer, but design constructable engineer. If your design goes directly to site and it works excellently fine without any problems, it is salutable. If your design invites multiple questions all time, every day, in that case this design is scrap. You cause a problem to site people rather than solving. That's why I say red lines. We cannot get quality due to complications created in designs. I got one question one day. I didn't get it. I mean, it's written on some site that there are 3 grades of concrete in some columns. Well, what do you mean by that? Can't you think what happens on site? Columns, you're saying 3 grades of concrete. Okay, you can take 10 grades of concrete, doesn't matter. But did you ever imagine how columns are cast? How shall batching plant operate? How shall your mixer operate even if there's no batching plant? Can you think that way? Can you imagine? We cannot imagine. Column concrete is very small. So if the whole slab, there are 3 slabs you are pouring on the same day, you can say this slab is having this grade, this slab, okay, that's acceptable. But column concrete should be my 5 cubic meter, 10 cubic meter, 15 cubic meter. And you want to add 3 grades to that, means one cannot cast them same day. And quantity of concrete in columns is very, very small. Nobody shall prefer different grades. That's why I'm saying complicating design is very easy. And there will be many, many explanatory people. Oh no, it can be done. Somebody says it cannot be done. Or somebody says, no, we can do this way and we can do that way. Without having any exposure to side problems, only reasoning is not enough. Only reasoning is not enough. We have to be very clear about this. Put off battery, please. Everybody can answer, everybody can question, but if answer is illogic, I say it is no use if my answer is illogical. I am on site, I was on site, it doesn't mean everybody on site, but you think I'm not a designer? Design is very easy to learn because you are not getting any information from all sources. You are just considering modeling, putting your parameters in and getting answers. But did you talk to building? Did you talk to structure? My question is that. You must say how to talk? No, you have to talk. You have to understand structure. You think when there was no software, designs were not done. Designs were done better than today. These were done. I see many videos, YouTube videos. Often I see engineering videos. If I find something, young guys, young engineers explaining everything, irrelevant to what is done, irrelevant to that. And they become teachers without having clear experience. Right? I'm not criticizing them. They should teach, but they should know first. Irrelevant talks without experience. Just telling, do this is right, this is not right, this is right, this is not right. Did you do it? How many projects have you done? You look so young. You're telling others what to do, what not to do. You have every right to tell. But if you have done it, if you have not done it, then you are not, you're just showing, this is my video. I have so many viewers, 25,000 viewers, okay, fine. But are you sure? My question is, can we know and apply quality standards complied elsewhere? For example, as I said, GCC countries or other Middle East countries on buildings and on plants facility. Particularly I am saying these countries because these countries have wondered, these countries have gone beyond expectations of practical world. I am not referring to USA or England because those people don't have that much money to spend on development works. You can't get that reliability from there as you could get from these countries. Only those countries who develop, you can get some feedback from them. West is not that zone in civil engineering. If somebody asks me, should I like to work here? I would say no. What's there? Civil engineering doesn't exist in those countries. Yes, there is a code, everything. That's different, but practically speaking, what's there? Can you compare those countries with development that happened in the Middle East? Never. If you go and see old buildings, old structures in these countries, you won't say that this is really that country. For example, UAE or Iraq. Can you compare with that? Never. That's why I say, if you have to learn civil engineering, you have to be different. Because you are a desert person, forest person you are. You're not a polished person. You have to stay in desert, you have to stay in jungle, you have to stay in remote area, you have to stay in such a location where others can't reach, where you sometimes do not find dogs. I am not giving you a ridiculous statement. It happens. Civil engineers and isolated engineers. If you are really a civil engineer, you are an isolated one. Civil engineer and society have distant relations, not coherent relations. And those who are not interested in such sacrifice, well, they should not enjoy civil engineering. I say enjoy, yes. Civil engineering is entertainment for me, maybe not for you. It is, because my concept is different. I help earth develop. Civil engineering for me is not just making money. No, money shall come, it shall go. It's not in my control. But whatever we do, as some engineers said, very veteran engineers said, I feel pleased, I feel very happy when I do design, and of course I get some money also. I keep that portion of money behind. I give that portion, I enjoy. I enjoy this design. That's what I'm looking for. Enjoy. Joy has no equivalent money value. If you enjoy something, this means you are immersed in that, only then you can enjoy. Immersion in that sea, this ocean is required, and which is very, very important profile, and which is in fact a kind of equivalent worship, super worship. We say work is worship, and that is worship we enjoy. Because when you pray God, you say, I am immersed in that worship. I am feeling very happy. Same way, work is worship. Civil engineering is worship because it takes you to origin of evolution. It takes you to desert. It takes you to places where others cannot visit, or they visit as tourists. So you are a tourist, you always go to origin, and you come out after development. It's different kind of world, civil engineering. And that's why I'm stressing, you are a builder, you are a maker. You are a maker of this world, group of civil engineers, profession of civil engineers. Origin, even there is no electricity, there is no mechanical world. Stones were built, walls were built, mud was used. It may not be qualitative, but it started. That's what I have to say. We have certainly worsening state of quality now because our opinions, our contemplation have devastated itself. Worsening state of quality of works is not digestible. We are working and we work for works. We perform for works and not for papers, not for systems. I think we have to come back a little from system of quality. We have to come back a little from quality system and go to works quality and then go forward again to quality system. We have to come back a little because we have missed something. And what we have missed? We have missed that quality system is required, it is mandatory, but we missed works quality. I've seen many audits of quality system, internal as well as external audit. Internal I don't trust much, but as for external third party is concerned, they seldom question about works. They conduct random checks only, and that random check does not mean anything. You can say renewal of documents, renewal of certification, I think is no meaning at all. It's not only system for which we work. It is for product we work. It's for building we work. It's for machine we work. It's for something we work. That is, we have to understand our world is different. We have to convert existing rock to artificial rock. You got my point? I'm saying we have to convert existing rock to artificial rock. Existing rock is natural stone. Artificial rock is concrete. Artificial rock is structural steel. We have to first manufacture steel and then to use it into buildings. That's what I'm saying. We have to worry about material quality, about product quality, about structural quality. I come to structural quality and how to improve that item. Structural quality, and it's not civil engineering structural, it's all structure. There are some marks. These marks can be obtained only after having conducted improvement into ourselves, into our performance. We must have patience in construction, in designs. We don't want to run with speed because speed won't work in construction. Speed won't work in designs. Many trials, many contemplations, because our work is going to perform for many decades, maybe 100 years more of time. We must have some patience. I cannot say today I construct a building, after 3 years I review it and demolish it. No, it doesn't happen. How to improve such mandated works quality to certain minimum requirement, at least to match with the minimum international requirements. And you say, why talking international? Everything is international. These days, what is not international? If you work in other countries for because maximum part of your life, how you're national as far as work is concerned? You know about this country, you know about that country, then you know about another country, then another country. So you have international experience, but we have worsening state of quality of concrete and material and equipment and gadgets and everything. How to improve such mandated quality to certain minimum required marks? So questions arise like this. And we know concrete component in constructions amounts to major percentage of cost, and therefore it becomes incumbent on us to care about quality of such component. Concrete, is very costly material in comparison to other materials. Concrete is very costly, but we should not forget it is in long run very cheap. Concrete can work up to hundreds of years and more, depending on how we do it, how we preserve it. And concrete means it is our, you can say, like kid. If I produce concrete, I produce it for many decades. It's not today I produce, tomorrow I say it's over. It's not electronic machine. It's not computer. It's not another machine or some consumable that tomorrow I have to buy again and consume it. It is concrete that shall work for me even after my death. Of course, it shall not work for me, but I am saying in my place, whoever is there, I should be there at that time, even after my death. Maybe my soul comes and sees this was my building, I did. It is still existing. It can happen. There's another part, I'm just trying to communicate that you have to be serious about that. Concrete, only material in physical world which is longest living. All other materials are recycled. Machine, even after 5 years, 10 years after, my car is over, I have to discard it now. Same way, something else you cannot use forever. But concrete is like your grandchildren, grandchildren, because your grandchildren may use your house, their grandchildren may use your house. So that's what I'm saying. It's like succession material. We say in our world, succession certificate, whose property it is now, to whom it goes now. So concrete is used by many your generations or whoever's generations. We have to keep that point in mind. We cannot keep one point, okay, I am constructing it today, tomorrow I will sell it to someone else. So if something happens, it happens to him. That is nonsense. Whoever may use it, but concrete is same. You you produce this, you are responsible for that. Concrete component is very expensive and it's very long journey material, and that is why we call it durable material, that it should work for that duration 50 to 150 to 250 years or whatever it is. It should be taken care of that way. Then so many times care it should be taken. If you want to keep it safe for so long time, we have to be serious about that. Our education should force us. Our system should force us. And we have to think in mind. It's not just I got a job and did it and run away from there, my job is over. Your job may be over technically, but don't forget, God sent you to this job to do it. It's not your home. We have to think that way. So what I say, concrete component in constructions amounts to major percentage of cost, and therefore it becomes incumbent on us to care about out of common and professional understanding. Why do have no seriousness in this regard? We have to invite seriousness. We have to be very serious about such issue of concrete material, because it is a resource. It's a resource, it's manufactured resource based on available natural resources that we extract from earth, lithosphere. We have to consider value of this resource. Rock is not available just in 1 year or 2 years. Sedimentary rocks consume, or these are produced in many decades. Metamorphic rocks are also produced in many decades. And igneous rocks, it's volcano. We have to respect these materials. That we use these materials for only few decades, which have been produced based on many decades. Just like we did not respect petroleum, we did not respect fossil fuels. We should not do this mistake to these materials. Worsening state of communication and coordination during working for engineering designs and executions or construction activities. We always are inclined to talk a lot. I do not mind it. Talk a lot. But if you don't talk a lot, you do a lot, I think that is beneficial. Talking is not a force, and if you don't have knowledge, then what do you talk? Gossipism? Gossipism is not required. Gossipism will not help. And those who have points, they talk little, but they talk points. I understand and I believe and I can prove that communication is very integrated part of engineering. Coordination is very much reliable part in engineering. These two work together, and these two work on every page of your book. These two work on every drawing and on our specifications. And if we do not frame ourselves or our work within controls of communication coordination, then we have no fixed destiny. We always divert. It may be engineering work, it may be work of designs, it may be work of executions or activities of construction. These terms, communication and coordination, do not work only as terms, but as additional systems, more important than whatever others. Lapse of communication, or you can say misinterpretation of communication, or you can say ignorance of communication, can lead to bad coordination, can I understand. I understand in profession, or in whatever way you can say, for information exchange, for information exchange, videos and audios are 00, and I'm sure this part of voice shall not be recorded, but I'm continuing to speak because if I stop, I may slip my tongue. So communication and coordination, you may say, these are our tracks, or tracks of tracks, or additional tracks of guard or signalman. If we communicate properly with good phraseology, phrasing, we can coordinate better. And coordination means considering all points, all aspects, what are required to be incorporated into one work. If even one is missed, work shall be defective and not directly suitable or fixed for purpose it was intended for. Therefore, engineer must realize use of communication, correct communication. No, don't shy. Learn it. If you want to be successful in profession at world level, communication plays an important role. And communication means total coordination. Without coordination, interdisciplinary world related works cannot be completed, cannot be taken care of. And when we work in designs, or we work in contract documents composition, or we work on sites, all these play important roles. That points cannot be ignored. Engineer should know how to work in communication, how to communicate properly to everyone. Engineer should have different strength of communications. Means you have to communicate to every class of people, every class of personnel, every class of vendor, every class of others. How to communicate that in best possible manner so that time is also not wasted. That communication you have to learn, and that can be learnt only based on experience, based on practice, based on possibility. Never look to face of others. They would do something for you. That is weakness engineering, that we never care for this. We never care for these two, communication and coordination, but these are very important. If you go to higher levels in your profession, you have to use these more and more because you have to connect with everybody. You have to satisfy demanded requirements, contracted requirements, and those cannot be done without power of communication, coordination. There is no way it can be explained a lot, it can be explained to unlimited lines. It's communication, coordination, but idea is enough. Idea is enough. When you can learn engineering degree, you can learn whole engineering syllabus. What is communication? Tell me. Is it that much value? I'm not saying that you have to think of grammar or translation, but message should be clear. That's what I'm saying. Don't write essay on that. I said pointed communication, informative communication, timely communication, interconnection of various problems, various details. That's a part of design. Even pre-design it is. That's a part of execution. If your drawings is not clear, it's misread by sight person. That person would carry out it. That's it, because my job, I am trying, I did it. That's why I say, do not be only desk office engineer. You are good engineer, it is no doubt, but first you must have a capacity to know problems on works. You cannot simply say you imagined something and it was right. Engineering has wide aspects. Engineering is widest seriousness and widest way where you can enjoy. And therefore, role of your job, role of engineer comes into powerful game, powerful play, powerful art. Engineering and engineer have two relations. Role of engineer has to be defined by engineer itself. Nobody else can decide about your role except your position's role. As an engineer, you are free to think. As an engineer, you are free to try. You are free to think. There is no other reason you cannot think. And that's a very important point. Yesterday, I'll now stop here on this talk because already 40 minutes have gone and I must have some opportunity to talk about yesterday activity. We were talking about some concrete. We are talking about concrete, and I think in addition to this document as I showed to you, talking this, and this was about nuclear power plant concrete structure, and I was in this page of last time, and it was said, I just repeat that, it was NUPC, it stands for this NRC model consists of one four scale model of pre-stressed concrete containment vessel, that is pre-stressed concrete containment vessel PCCV of an actual nuclear power plant in Japan, whatever it is given, one of four units comprising. Okay, now design pressure for model and for prototype is 0.39 MPa. Features and scale of PCCV model were chosen so that response of model would mimic global behavior of prototype, and local details, particularly those around penetrations, would be represented. Model includes a steel liner anchored to concrete shell. Model includes a steel liner anchored to concrete shell. Details of design and construction are reported in test report. Overall geometry, (720) please. Yes. You can say it is 720 centimeter here, and nautical 350 centimeters depth here, 350 centimeters, and it is 1640 centimeter, 16.4 meter is this vertical height, and this curve shape is 5.65 meters, and of course this here you can say this is quite heavy, of course, and thickness is this wall thickness 325 mm, Internal diameter is 1075 centimeter. This means 10.75 meters. And you can say this is title is Models Tested by Sandia National Laboratory. Pre-stressing levels for model tendons were selected so that net anchor forces, considering all losses due to anchor seating, elastic deformation, creep, shrinkage, and relaxation at time of limit state test, match those expected in prototype after 40 years of service. It says elastic deformation, creep, shrinkage, and relaxation at time of limit state test match those expected in prototype after 40 years of service. Construction started in 1997 and was completed in 2000. Concurrent with construction of model, Sandia installed nearly 1,500 transducers to monitor strain, displacement, forces. Consisted of a series of static over pressurization tests. Static over pressurization of tests. This is pressure testing of model consisted of a series of static over pressurization tests of increasing magnitude. Beginning with system functionality test to 0.5 PD. Series of tests combined structural integrity and integrated leak test. Structural integrity combined tests means series of tests combined structural integrity and integrated pressurized to 1.25 PD and after holding pressure for approximately 1 hour, model was depressurized to 0.9 PD and held at that pressure for 24 hours. During this period, a leak rate less than 0.1% mass per day was calculated, essentially demonstrating that model was leak tight. For limit state test, model was pressurized for limit state test. For limit state test, model was pressurized in increments of approximately 0.2 PD to 1.5 PD. Then in increments of approximately 0.1 PD to 2.5 PD. At this pressure, a leak test of 1.63% mass per day was calculated. 1.63% mass per day was calculated, indicating that model was leaking, most likely from tear in liner in vicinity of equipment hatch. And it was concluded that model had functionally failed, was not as leak tight as required between 2.4 and 2.5 PD. In order to collect data on inelastic response of structure and to observe a possible structural failure mode, pressurization continued to in steps of 0.05 PD. Pressure was increased to slightly over 3.3 PD before leak rate exceeded capacity of pressurization system and test was terminated. At maximum pressure, local liner strains approached 6.5% and global hoop strains at mid-height of cylinder averaged 0.4%. Large tears were observed near equipment hatch, although Extensive concrete cracking was reported at some locations. There was no indication of tendon or rebar failure, and data showed that no tendon strains exceed elastic limit, while only a few dozen rebar strain gauges showed strains in excess of 1%. With the objective of observing large inelastic deformations, for comparison with analysis and witnessing structural failure mode of PCCV model, interior surface of liner was then sealed with an elastomeric membrane. Model was filled with water to 1.5 meter from dome apex and remaining gas pocket repressurized. A wire break was detected for pressure slightly higher than 3.3 PD peak pressure achieved during LST and at an effective pressure of 3.63 PD. PCCV model ruptured suddenly and violently. Main lesson learned from this remarkable experiment is that pre-stressed concrete containment of this type can be regarded as having a pressure capacity around 2.5 times design pressure in terms of leak tightness and around 3.5 times design pressure in terms of ultimate limit load. This NRC 2006. So I say what says main lesson learned from this remarkable experiment is that a pre-stressed concrete containment of this type can be regarded as having a pressure capacity around 2.5 times design pressure in terms of leak tightness and around 3 times design pressure in terms of ultimate limit load. This associated analysis. Pre-test production analysis were also completed and published. A number of regulatory and research organizations were also invited to participate in a pre-test round robin analysis to perform predictive modeling of response of model to over pressurization. 17 organizations responded and agreed to participate in pre-test round robin analysis activity. These are all, some references. I'm not going to speak all this. PVC sitte response quantity driving limit state of vessel is radial expansion of cylinder. PCCVC test showed that response quantity driving limit state of vessel response quantity driving limit state of vessel is radial expansion of cylinder. This response must be predicted correctly in order to approximately local response mechanisms that are driven by cylinder expansion. Interestingly, a conclusion of Posted's analysis was that average radial expansion or hoop strain of cylinder was predicted very accurately by axisymmetric analysis. Axisymmetric post-test analysis also gave evidence that an appropriate modeling of tendon friction behavior is crucial. A detailed analysis led to conclusion that considerable both effects of discrete crack and elevated local strains, a liner tear could have been predicted to nearly occur as early as 2.8 PD. One question which remained following PCC test was how temperature loading might have affected result of test. In an attempt to answer this question, Nuclear Energy Agency of OEC recognized it as an international standard problem and sponsored analysis in view of its resolution. 11 organizations, including several participants in pre-test round robin, participated in ISP result of which are reported by this document. Unfortunately, the round robin analysis to perform the modeling of response model to our pressurization. 17 organizations responded and agreed to participate, and that results along with individual participant reports which resulted in following observations. Predictions of elastic response. Predictions of elastic response. Predictions of elastic response were for most part very consistent up to onset of global yielding hoop, which appears to occur around 2.5 PD. Prediction of response diverge significantly beyond this point, with response varying by a factor of 3 to 5 or more at a given pressure. For failure predictions based on material failure of steel component, liner, rebar or tendons, average predicted pressure is at failure is 3.6 PD. Approximately half participants predicted failure based on structural disruptive parts or tendons, while approximately half participants predicted functional failure. A remarkable example of evolution is related to aircraft crash for generations. Two NPP's conventional design criteria for reinforced concrete were used, associated to load cases of business or military aircraft crashes. After 2001 September 11 attack, it was recognized that a malevolent commercial aircraft crash should be considered in safety assessment of NPPs and taken into account in designs NPPs to be built in future. However, it is also recognized that when dealing with extreme loads such as generated by commercial aircraft crashes, more realistic criteria should be taken into account according to ultimate capacities of concrete wall capacities against perforation. Perforation of concrete walls by rigid missiles has been studied for decades. Different empirical formula were proposed by different authors. A comprehensive review of each is presented. A widely used formula is known as CEA or EDF formula, which was established in 70s. An improved formula has been proposed by Buzzard with a significantly larger validity domain. At moment of generation 2 NPPs, I'm talking about generation 1, 3, generation 2 NPPs design, rather small aircraft engine were considered, which were regarded as rigid missiles. They were regarded as rigid missiles and corresponding formula were used. For generation 3 NPP, larger engines are considered. However, researches carried out in last 3 decades gave evidences that aircraft engines should not be regarded as perfect rigid missiles, and consequently a larger interest has been paid to achieve a realistic estimate of their actual perforating capacities. A series of experiments was carried out in Germany in 70s known as McMahon test. Famous experiment was also carried out by Sandhya National Laboratories, consisting of crashing an actual military aircraft on a concrete wall. Recently, an experimental campaign was conducted by Technical Research of Finland in frame of an international cooperative program which provided matter for an international benchmark. Let us go on. I think I missed it. This is the, let me see. Just in the piece. It's gone somewhere here. I think it's stuck somewhere. Generation 10 pp's. This was also done. Concrete wall capacities against perforations. Formula which established in the range of formula has been proposed. Remain. So generation 2 is also here considered. So this has gone. This is gone recently, and when okay, this is there cooperative programs which provided method for international benchmark. Okay, this is here international benchmark under this one. Analysis carried out by Sugano led to amend empirical formula for rigid missiles so that they are applicable to aircraft. Let's go there now. So it's that. Analysis carried out by Sugano led to amend empirical formula for rigid missiles so that they are applicable to aircraft engine impacts. Such amended formula are available somewhere. For instance, in order to be protected against perforation Required wall thickness is only 70% of what is necessary according to necessary, and that is, for instance, in order to be protected against perforation, required wall thickness is only 70% of what is necessary according to rigid missile formula. Concrete wall bearing bending capacities. Concrete wall bending capacity. As opposed to perforation, issue, assessment of concrete wall bending capacity is not addressed through empirical formula. Physics of phenomena can be accurately modeled. Loading force is generally established through real formula, and wall capacity is evaluated through usual ultimate limit state acceptance criteria. About commercial aircraft, it should be pointed out that they were initially aimed by RERA. Consequently, physics of their crashes conceptual approach ever even better than military aircraft crashes do, and not surprisingly, method still applies. Regarding acceptance criteria, it was recognized that design basic condition criteria, such as adopted for design against military aircraft crashes, were not appropriate to assess effects of extreme loads such as generated by commercial aircraft crashes. For this purpose, commercial aircraft crashes were categorized as a design extension condition. And appropriate criteria were established corresponding to a more realistic approach of impact effects on a structure. A simplified comparison of DBC and DEC criteria is summarized. National practices vary so that it is not possible to establish here a comprehensive and accurate comparison. Values in this table should be regarded as representative of values that are retained by certain following documents. These are under Harris comparison DBC and DC criteria for aircraft crash. DBC is design basic condition and DEC is design extension condition. Design basic condition and design extension condition. We have various parameters here. We are comparing this between DBC and DEC. Concrete strength, strain rate effect for concrete confinement effect, age of concrete strain capacity, steel elastic strength, steel ultimate strength, steel ultimate strain, Concrete strength in basic criteria, that is for military one, and extension is for commercial one. So this is concrete strength, and that is FCK over gamma C 1. You can say it is concrete strength FCK of YC, and here is FCK of FCM. These are strain rate effect for concrete. Strain rate effect for concrete is 1, and in other case is 1.1 or 1.25. Concrete confinement effect is 1. Here is 1.2, that is for commercial aircraft. Age of concrete 28 days in this case, and this 1, and 1.1 is 100 days. Concrete strain capacity in first case is 0.35 to 0.5%, in other cases 0.5% to 1%. Steel elastic strength, this is about steel elastic strength, and then ultimate strength, and then steel ultimate strain 0.8% to 1%. Other cases 0.5%. And then it says steel is ducted vibration. Both military and commercial aircrafts, both military and commercial aircraft crashes result in structure induced vibration. In structure induced vibrations that should be accounted for in safety assessments. Frequency content of dynamic load, we have to account them for in safety assessment. Frequency content of dynamic load by crash is still an open issue. Refined modeling of aircraft structure crash indicates that high frequency content ignored by RERA approach should be taken into account in load function. It doesn't mean that an additional input should be added on top of RERA's load curve, but that this load curve should not be as smooth as it appears. High frequency content of loading force and corresponding wave propagation in concrete structures, in particular energy dissipation along wave path, are matters of research for coming time. In structure transferred vibrations are crucial for equipment assessment. A usual way of dealing with them is to set a comparison with seismically induced vibrations due to rather small aircrafts that were considered for generation 2 design. It was possible to substantiate that aircraft crash induced vibration were covered by seismically induced vibration. With aircraft that are now considered, intrinsic high frequency content of aircraft crash induced vibration should be addressed per se. A favorable feature of those high frequency vibration is that they generate very small displacement. A favorable feature of those high frequency vibrations is that they generate very small displacements. There is a consensus among experts on fact that an approach based on induced displacement is much more appropriate than a conventional seismic approach based on accelerations when addressing equipment safety assessment issue under aircraft crash condition. As a floor response spectra at top of CMU specimen, frequency this way, pseudo acceleration. So earthquakes now, to certain extent, there's similarity between aircraft crash and seismic input motion issues. In both cases, for existing NPPs, plant design was established under design basis conditions, and it should now be assessed under extreme conditions of design extension conditions. Experience and experimental feedback. Several cases of seismic motions that approach or exceed design basis earthquake were reported before Fukushima in Japan and to a lesser extent in US. As a matter of fact, more challenging seismic input in motion recorded in NPP at occasion of Great East Japan earthquake was not at Fukushima but at Onagawa, much closer to epicenter than Fukushima. Feedback of experience of these events is that NPP concrete structures are actually very robust against seismic input motions. This is due to the fact that nuclear industry design criteria encompass large margins, resulting in fact that when designed for a given input motion at NPP concrete structures is capable to sustain at least 3 to 4 times this design input motion without significant damages. I repeat, feedback of experience of these events is that NPP concrete structures are actually very robust against seismic input motions due to the fact that nuclear industry design criteria encompass large margins, resulting in fact that when designed for a given input motion of NPP concrete structures is capable to sustain at least 3 to 4 times this design input motion without significant damage. Evidence of such large margin was provided by Kashawaki, Korea, NPP in 2007, although recorded motion of raft of Unit 1 was 0.68 G for a design value of 0.27 G. Only visible damage on concrete structure was a thin crack. This feedback of experience is confirmed by experimental outputs. A comprehensive review of experimental results available in 2003 on NPP concrete robustness against earthquake has been presented by IAEA. More significant experimental campaign on typical nuclear wall was carried out in Japan, USA and Europe. More recently, smart experiment was carried out in France and accompanied by an international blind prediction benchmark regard. Seismic response analysis. Seismic response analysis. Current situation is that existing NPPs were designed for a given seismic input motion and that nuclear industry design practices provide large margins, principally implicit beyond design. Actually, situation is similar for design of generation 3 NPPs. A challenge for nuclear industry is now to make those margins explicit so as to identify a beyond design input level until plant is safe. Design DBL under DB conditions response of concrete structures is generally supposed to stay in elastic regime. Under DB conditions, response of a concrete structure is generally supposed to stay in elastic regime. Accordingly, conventional industry behavior factors are disregarded. Although associated criteria are those of an ultimate limit state compatible with cracking and or even R bars yielding. Inconsistency is sustainable because most structural elements stay eventually in elastic regime under DBE. Very few of them reach acceptance criteria. Under extreme input motions, friction of an elastic regime for computing structural response is not possible anymore. Because by definition, structures a practical approach of non-linear response of concrete structures, such as widely used for seismic assessment of existing NPP around the world, is presented by IAEA 2003. However, this approach relies on elastic response computation and is therefore limited to relatively small dBE exceedance. When addressing significant dBE exceedance, non-linear behavior should be represented. In this regard, an example of universal engineering design practice that accounts for non-linear behavior is given by geotechnical engineering, such as it was established in the 70s on basis of equivalent linear relationship. Development of a similar methodology addressing concrete structures was recommended by IEA before Fukushima days. Concurrently, in order to address an aimed domain of nonlinear response, it is necessary to have not only a realistic representation of soil and structural behavior, but also of seismic input motion. Description of seismic input motion. It means that conventional design response. Conventional design response spectra such as NRC 1973 or EUR 2012 or Eurocode 2005 spectra, which provide appropriate load for design purpose, are not appropriate for dealing with extreme events for several reasons. On soil sites, site response is controlled by soil behavior. Consequently, due to nonlinear soil response, spectrum shape of input motion is dependent on seismic input level. On soil sites, site response is controlled by soil behavior. Consequently, due to nonlinear soil response, spectrum shape of input motion is dependent on seismic input level. Conducting nonlinear analysis generally requires concurrently that it be transient analysis, meaning time history input motion should be available. There are engineering tools that enable to derive accelegrams from response spectra, but state of art is precisely that such signals should not be used for non-linear analysis, except if generated with as mentioned above. There is a certain lack of consistency, at least in some countries, and in nuclear industry approach. As mentioned above, there exists certain lack of consistency, at least in some countries, in nuclear industry approach or of seismic qualification of concrete structures, because on one hand seismic response is computed by assuming an elastic behavior of concrete, but on other hand acceptance criteria are those of ultimate limit states. Furthermore, these criteria are expressed in terms of forces or stresses, while according to state of art, purpose of evaluation of seismic capacity should be to analyze strains induced by postulated input motion and to compare them with ultimate acceptable strains. Basically, as pointed out by IAEA 2003, it means that approaches oriented to strain evaluation, displacements approach, are more relevant than those based on stresses evaluation forces approach. Such an evolution of criteria towards displacement or strain approach is in line with current development of standards that go towards a wider use of performance-based criteria in place of acceptance criteria based on computation of stresses or forces to be compared to allowable stresses or forces. Performance-based criteria are preferably expressed in terms of strains, either global drift under earthquake load or local strains on R bars and concrete under aircraft crash. Criteria are modulated according to required function of concrete structure under consideration: leak tightness, supporting of equipment stability, etc. An interesting and exemplary use of performance-based criteria is presented in ASCE 4305 Standard 2005. For instance, depending on accepted damage in case of an earthquake, depending on accepted damage in case of earthquake, acceptable drift for a concrete movement resistant frame varies from 0.5% essentially elastic to 2.5% stable short to collapse. 0.5% drift associated to an essentially elastic behavior of structure draws attention because for such a drift, forces computed on basis of an elastic response exceed acceptable forces according to conventional criteria. It reveals once again that ignoring cracking effects that occur for even low levels of input motion is not realistic. Induced vibration. Purpose of seismic response analysis of NPP concrete structure is not only to discuss structure qualification but also to derive seismic input motion that are transferred to this transferred motion is generally represented in form of flow response spectra. As pointed out by IAEA 2010, key point with flow response spectra is that they are very sensitive to small structural non-linearity. IAEA conclusion is that even for input motions that do not exceed dB, those nonlinear effects related to micro cracking or cracking of concrete structures should be taken into account of FRS generation. An illustration of this effect is provided by outputs of CMU's experiment carried out in France on CA shaking table in 90s and extensively discussed at occasion of an international benchmark raised by IAEA. During first run of experimental campaign under an input motion 0.4 G that did not exceed acceptable input level according to nuclear practice 0.7 G, a significant frequency shift towards lower frequencies was observed. A fortiori when dealing with BDBE, it is certainly necessary that structural non-linear effects are properly included in finite NPPS. Of 437 operating units, approximately 83% have been in operation for 20 years or more and 46% for 30 years more, which are mostly generation 2. One key concern that could affect continued operation and development of nuclear power relates to impact of aging on plant performance. Unlike mechanical components or electrical equipment that can be replaced concrete, civil structures either cannot be replaced or would be very difficult to replace. As noted previously in this paper, NPP concrete structures are designed, built, and operated to standards that aim to reduce likelihood of release of radioactive materials to levels as low as reasonably achievable. The NPP, however, involves complex engineering structures, sometimes operating in demanding environments that potentially could challenge respect to concentric structures. NPP, however, involves complex engineering structures, sometimes operating in demanding environments that potentially could challenge high level of safety. That's why I'll miss one line. That this could challenge high level of safety, that is safety margins required of plant throughout its service life. With respect to concrete structures, age-related degradation may affect engineering properties, structural resistance capacity, failure mode, and location of failure initiation that may in turn affect ability of a structure to withstand challenges in service. When a concrete structure degrades, function of many factors, including constituent materials, location, means it may be coastal or inland, climatic condition, temperature, moisture, and presence of external agents, aggressive ionic species. NPP concrete structures are composed of several constituents: concrete, mild steels, reinforcing, rebar, pre-stressing systems that in concert perform multiple functions: foundation, support, containment, shielding. Some concrete structures, the spent fuel pool and containment also can include a metallic or polymer liner to provide leak tightness or a pressure boundary. Concrete material durability can be limited by adverse performance of either its cementitious cement-based matrix or aggregate constituents under attack. In practice, these processes may occur concurrently to reinforce each other. In nearly all physical and chemical processes influencing concrete durability, dominant factors involved include physical attack mechanisms involve degradation of concrete due to external influences and generally involve cracking due to exceeding concrete tensile strength or loss of surface materials. Salt crystallization, freezing and thawing, thermal expansion, thermal expansion, thermal cycling, abrasion, erosion, cavitation, irradiation, fatigue or vibration, biological attack and differential settlement. So many properties that are questioned here. I repeat, physical attack mechanisms involve degradation of concrete due to external influences and generally involve cracking due exceeding concrete tensile strength. A loss of surface material, namely salt crystallization, freezing and thawing, thermal expansion, thermal cycling, abrasion, erosion, cavitation, irradiation, fatigue or vibration, biological attack and differential settlement. Chemical attack involves alteration of concrete through chemical reaction with either cement paste or coarse aggregate that generally occurs at exposed surface regions of concrete. Cover concrete but with presence of cracks or prolonged exposure, it can affect entire structural cross section. Chemical attack may occur in several different forms. Efflorescence and leaching, attack by sulfate, acids or bases, delayed ettringite formation, and alkali aggregate reaction. Degradation of steel rebar can occur as a result of corrosion, irradiation, elevated temperature or fatigue effects, with corrosion being most likely form of attack. Post-tensioning systems are susceptible to same degradation mechanisms as rebar plus loss of pre-stressing force, primarily due to tendon relaxation and concrete creep and shrinkage. Metallic liners are susceptible to corrosion, namely areas of moisture accumulation and fatigue at locations of stress. Intensification, namely shape changes and structural attachments. Non-metallic liners can degrade as a result of impact loads, stress concentrations, or reflective cracking, namely physical and chemical changes in concrete. Operational experience. Operational experience. In general, performance of NPP concrete structures has been very good. However, several of these structures have experienced degradation that has required a remedial action. Initially, many problems identified occurred early in life, were addressed at that time, and were related to errors in material selection, design or construction, cracking of pre-stressing anchor heads due to stress corrosion cracking, containment dome delamination, due to design and material deficiencies, low concrete compressive strength, excessive voids or honeycomb in concrete, and misplaced rebars. As NPPs age, degradation related problems are occurring due to environmental effects, cracking and spalling of containment concrete due to freezing and thawing, corrosion of rebar in water controlled structures, cracking, moisture intrusion, and leaching of concrete corrosion of metallic liners, pre-stressing tendon wire failure due to corrosion, concrete cracking due to alkali silica reactions, and leaking of borated water from spent fuel pool and refueling cavity liners, potentially causing concrete erosion and corrosion of embedded carbon steel. In order to ensure continued safe operations, it is essential that effects of degradation of plant structures as well as systems and components be assessed and managed. Operating Operating experience has demonstrated that periodic inspection, maintenance, and repair are essential elements of an overall program to maintain an acceptable level of reliability over service life of NPP concrete structures. Knowledge gained from conduct of an in-service condition of assessment. Knowledge gained from conduct of an in-service condition assessment can serve as baseline for evaluating safety significance of whatever degradation that may be present and defining subsequent in-service inspection program. Knowledge gained from conduct of an in-service condition assessment can serve as basic as baseline for evaluating safety significance of degradation that may be present. and defining subsequent in-service inspection programs and maintenance strategies. Effective in-service condition assessment of a structure requires knowledge of expected type of degradation, where it can be expected to occur, and the application of appropriate methods for detecting and characterizing degradation. Assessment program include review of as-built drawings, that is number one. We have many here. We may say many have this chapter. Review of as-built drawings and other information pertaining to original design and construction information, so that information such as accessibility and position and orientation of embedded rebar and plates in concrete is known prior to site visit. Sorry. It's known prior to site visit. 2. Detailed visual examination of structure. To document early obtainable information on instances that can result from or lead to structural distress, namely crack mapping. Third is determination of need for additional surveys or application of destructive and non-destructive testing methods. Four, analysis of results. And 5, preparation of a report presenting conclusions and recommendations. Techniques for establishing time-dependent change. Technique for establishing time-dependent change, such as section thinning due to corrosion or change in component geometry or material properties involve monitor or periodic examination and testing. General guidance for developing a condition assessment program for managing aging of NPPE concrete structures has been provided by organizations such as International Atomic Energy, Electric Power Research Institute, and International Union of Laboratories, and experts in construction materials. International Union of Laboratories and construction experts in construction materials, systems and structures, and Nuclear Energy Agency Committee on Safety of Nuclear Installations. Individual countries also have developed their own program addressing concrete structures. Testing and insert structures. In US as well as several other countries, Belgium and Spain, testing encompasses conduct of an integrated leakage rate of containment structure to provide periodic verification of leak tight test. Leak tight, leak tight integrity of primary reactor, containment as wall as system, and components that penetrate containment. Associated with leakage rate test is general visual inspection of access interior and external surfaces of containment structures and components to uncover any evidence of structural deterioration. So it says conduct of an integrated leakage rate. Let me repeat this. Testing in service inspections are utilized to assess condition of NPP concrete structures. In US as well as other countries, Belgium and Spain, testing encompasses conduct of an integrated leakage rate test of containment structure to provide periodic verification of leak tight integrity of primary reactor, containment as well as systems, and components that penetrate containment associated with leakage rate test is general visual inspection of accessible interior and exterior surfaces of containment structure and component to uncover any evidence of structural deterioration that may affect either containment structural integrity or leak tightness. Subsequent IWL of section 11 of ASME boiler and pressure vessel code provides regulatory requirements for inspections and repair of NPP, reinforced and post-tension concrete containments. Accessible concrete surfaces are examined. structural integrity test and so it says that may affect either containment structural integrity or leak tightness. Subsection TWL section 11 of ASME boiler pressure vessel code provides regulatory requirements for inspection and repair of NPP, reinforced and post-tensional concrete, containment SME. Accessible concrete surfaces are examined visually, generally, and detailed at 135 years following containment structural integrity test, and every 5 years thereafter for evidence of damage or degradation. Acceptance of concrete in accessible area. Inaccessible area, namely foundations, is to be evaluated when conditions exist in acceptable inaccessible areas, and that could indicate presence of or result in degradation to such inaccessible areas. One approach is to sample groundwater adjacent to structure of interest, namely pH and chloride and sulfate ion concentrations. Unbounded post-tension tendon system. Unbounded post-tension tendon system examination schedule is some for an concerted and involves measurement of so we can see then one approach is to sample groundwater adjacent to structure of interest pH, that is pH and chloride and sulfate ion concentrations. Unbound post-tension tendon I think let's take a gap of 5 minutes. Better in that case, you can take some time and back. Meanwhile, I will be back in that case. We have to wait. Go and come back in a good way, right? Better.